or November here. Okay, last time we talked about arc ignition and the fact that it occurs by touch start or by high frequency overlay. You've got to generate free electrons in that space in between. And by touch start, it's basically the resistive heating of little asperity contacts. And essentially, as you're breaking those contacts, the resistance goes up. And as the resistance goes up, the heating value goes up. The heating value goes up, and you can get to the vaporization temperature of the metal quite readily. With only 1 or 2 volts, you basically blow things apart as you're separating those things. High frequency overlay, basically there's a resonance effect if you get to 100 kilohertz or so, where you basically vibrate the electrons off the atoms in the gas, the surrounding gas, and so you can get a plasma that way. Once you get a conducting plasma, then the power supply takes over and pumps whatever current you set it for, 100 amps or 200 amps or whatever through there. Then we started talking about heat flow, and I mentioned that the Fourier number, which is just x over square root of alpha t, provides a quick, simple method of determining whether the part is thermally thick, thermally thin, or somewhere in between. And somewhere in between means that you may actually have to do some sort of more sophisticated analysis. It takes a little bit of judgment to know what we mean by the results of the Fourier analysis, and I gave you this plot of convergent heat flow and divergent heat flow and optically thick and optically thin. But then I realized, I think I mentioned to you, there's a building down here in downtown Boston where they're making some really heavy welds in this. This is like a 40-story building. It has a 60-foot overhang on about the 10th floor over some other buildings. And so there's this really massive, they call it a knuckle, but it's a very complex connection with, you got a column coming up this way, you got beams going across this way, and you got some other supports at a diagonal, of course, coming into this to carry these 2 knuckles carry the whole weight of the overhang. And they had some cracks, and so back in September, actually maybe it was August, I went to look at a couple of these cracks, and then we got into a big debate as to why the cracks were occurring and how to repair them and stuff. But anyway, the column itself, this would be the center line of the column, and the column walls of this box column are 7 inches thick of steel. That's pretty massive. And it turns out just about a week and a half ago, some engineer who's never seen the job, whose company recommended the wrong welding wire to weld this with, a higher strength version than was really needed, which is actually one of the reasons the cracks were occurring. Basically said, oh, well, we never would have recommended that wire. I said, well, I have this fax from your firm on April 23rd where you recommended this wire. Oh, well, that's because even though we're the application engineering group, we didn't know what the application was. I said, I didn't actually say it to him because I was trying to get information from him, and I didn't want to tell him he was an idiot. But and this is on the web now, right? That he's an idiot. He is an idiot for an applications group giving out a recommendation for a welding electrode when they don't even know what the application is. Okay, but in any case, so he used the wrong electrode. Now the question is, what do you do with it? Well, this guy says, okay, rip out 2,000 pounds of weld metal. Well, 2,000 pounds of weld metal is not so bad, except it sort of means you got to go back and rebuild most of the building that you've already built. Okay, so this is millions of dollars of repair work. And I said, well, why do we have to repair the welds that haven't cracked? Well, these guys weren't doing a good job. I said, well, how do you know they weren't doing a good job? Frankly, you look at these welds, and they're the best looking welds I've ever seen in the field. Okay, they're beautiful. They look like shop welds, and welding, up in a skyscraper with the wind blowing on you and everything. He says, well, they said that they preheated these things, these columns, to 250 degrees, and when they came back the next morning, there was still 150 degrees of preheat in the material. And he says, I've never seen, unless you insulate it, steel hold that type of temperature. I said, well, have you ever welded 7-inch thick steel before to check the preheat? And he wouldn't answer that question. But I did the calculation, Actually, I didn't do the calculation. I've kind of done this calculation enough times. I did it just now, actually. 7 inches times 2.5 centimeters per inch is about 18 centimeters. So that's the thickness in centimeters. If we're talking 12 hours, let's say they left at 7 o'clock at night and they came back at 7 o'clock in the morning, the guy put his hand on it and he had left it at 250 degrees preheat, and it was now down to 150, which means you don't want to hold your hand on it too long or you'll burn yourself. Actually, I'm sure they probably measured it. That's about 40,000 seconds. I go through x to the square root of alpha t, 0.1 centimeters squared per second for steel, times 40,000 is the square root of 4,000. Square root of 4,000, if I did that approximately right, is about 60. Now you see I've done a little rounding off here, right? It's actually 3,600, not 4,000. And it's not 18 centimeters, it's 17.5 centimeters. Who cares? The point is, I've got x is equal to 60 centimeters versus 18 centimeters up here. Now this is a simple linear heat flow. And what they've told me is one guy, the welder, claims he left it, and I don't know if it's exactly 12 hours or what, but he left it and there's no heat flow this way because this is the mirror plane. There's another beam, another part of the box beam on the other side. So there's only heat flow out this way. Now, if this is room temperature, which back in August was 70 degrees, 80 degrees at night, and this is 250 degrees, and the guy claims when he came back in it was 150 the next morning. Is that reasonable? Well, it turns out for a planar solution like this, it turns out a Fourier number of 1, which is would be, well, I'd have to put 18 squared, which is what, 376 or 96, whatever the number is. No, 326, right? Is that right? 324. Is equal to the square root of 0.1 times whatever the time is, so it's 3,224 seconds or something, whatever that is. That's at 10, there's a 10% rise. I'm sorry, I'm going the wrong way. This is if I was heating from that surface. It's 1 minus the Fourier number, so I'm going to have 250, and it's going to be a 10% drop in temperature at a Fourier number of 1, and at a Fourier number of 2, it's going to be about a 20 or 25% drop, and a Fourier number of 3, I'm going to have a 50-60% drop in temperature. Well, what do I have? I have 100 degrees over 180. That's about a 60% drop in temperature. That's a Fourier number of 3. What's my Fourier number here? 3. What that welder said, he found it at 150 degrees the next morning, and I just confirmed he's absolutely right. And he wasn't lying. And this application engineer for a major welding firm in another state that will go unnamed, but they're all in Ohio. No, they're all in Ohio, but the largest ones are in Ohio. Okay, and I won't necessarily tell you their names. He just shot from the hip, and he says, "Rip it all out." I said, "Well, did you do a calculation?" "No." "Do you have any data?" "No." Okay. But, you know, he just told people to delay the project. What's this project worth? $200 million? Delay the project 2 or 3 months, spend several $1 million. What's all that's going to cost? You know, it'll be $10 million when it's all done, if you talk about the delay in the project and everything else, without even having done a calculation, because he doesn't believe the guy. Well, you know, I'm sure the welder who did this can't do this calculation either. But the welding engineer, who's head of applications for this company, can't do this calculation, but you can. So anyway, that's how you use it, okay? And I'm not saying you're going to know how to use it and kind of realize how the Fourier number drops and things until you've done these things and looked at heat flow problems a number of times. But it's really, if you get into this, it's not that hard. And it also works for mass flow. Anybody have any questions? That's a specific example like I said, I go through these types of calculations about once a week for some sort of thing, whether it's a student's thesis or a project like this or whatever. Okay. Now it turns out that the heat flow in welding, there have been several major advances, and it turns out most of them have something to do with, here at MIT, at least some connection. But the simplest heat flow analysis, which you'll find not by someone here at MIT, but you'll find in textbooks. There are textbooks. I could have brought in 2 textbooks that mathematicians solving the diffusion equation. One's called Crank Diffusion in Solids, and that's for mass diffusion, you know, diffusion of atoms in crystals and stuff. Another one is Carslaw and Jaeger, some Australians, mathematicians who wrote a book on heat conduction in solids. Well, it's just the same thing. They're solving it for planar geometry, cylindrical geometry, spherical geometries, thick plates, thin plates, you name it, where they can come up with simple or analytical solutions. And these books were done back in the 40s and 50s before people had digital computers. Nowadays, someone just plugs in the boundary conditions in a computer and they pop out some answer they don't understand. But the simplest solution is just a one-dimensional planar solution where I have 2 bars and I have a planar heat source which has an intensity of some heat Q divided by some area A. So that's going to be a watts per square centimeter type of number. Well, what's this? This is based on something like friction welding. I bring these 2 rods together and it's a planar heat source. So this is basically just a simple friction welding problem. And the solution is the temperature dies off, it starts out at some peak, and over time, or you make the weld in a friction weld, you turn it off, it starts out at some T is equal to 0, you've got a lot of heat at the interface, and basically it's just a Gaussian decay. And the area under that curve, which I haven't drawn very well, the area under these curves should all be the same, as long as I don't keep putting heat in there. And that's equal to all of this stuff. This is the heat I put in, 4 pi alpha T, well there's the alpha T, that you always, that's the part of the Fourier number here, 1 over rho C sub P, exponential of a pure number, which is, this is the Fourier number divided by 2 squared, whole thing squared, okay? So it's this is just a Gaussian, exponential minus x squared. It varies with time, and it's a decaying Gaussian. So the heat diffuses out essentially like a random walk process, if you're familiar with Gaussian being a kind of a statistical probability distribution. You can do the same thing in 2 dimensions where you have a linear heat source, and this is not all that different than something like a laser electron beam weld where you have a very deep penetrating line source. And now your Gaussian is a 2-dimensional Gaussian radiating away in 2 dimensions from that linear heat source. Okay? It turns out here I had a 1/2 power for this. Here it's a 2/2 power. And here I have a Q over delta. Instead of Q over area, I have Q over, this is heat per unit length of the line heat source. This is the intensity of the heat along the line. And I can go to a 3-dimensional heat source by analogy, and I have buried in the middle of a plate at 0, 0, 0, where I have x, y, and z coordinates here, I can have heat radiating away, decaying as a Gaussian of minus r squared, where r is just square root of x squared plus y squared plus z squared. So going away in a spherical coordinate system, if you will, I basically have heat decaying as a Gaussian, and that Gaussian spreads out over time. In this case, it's just Q. It's not divided by delta. It's just the intensity of that spot, because that's a mathematically simple spot. And here I have 3/2, which maintains my dimensionality. Alpha t, this 4 pi alpha t has dimensions of centimeters, right? Or I'm sorry. It has dimensions of centimeters squared, which if I take the square root of that has dimensions of centimeters. So I keep my same dimensionality in here the whole time. Those are all stationary heat sources, and those before 1940 or so you could find in a handbook, and you still can find them in handbooks. A guy named Daniel Rosenthal was in Germany right before World War II in the 1930s. And he was Jewish. He didn't like what was going on with the Nazis. And so he moved first to the Netherlands, and then the Nazis were getting kind of close to the Netherlands, and so he was trying to get to the United States. And he ended up first having to go to Morocco in 1939 or so before he could get to the United States. When he got to the United States, the place he went was over here in Building 2. Well, not Building 2, Building 3. It's one across the Great Court from my office, right? He was in the mechanical engineering department at MIT. While he was on the run through the Netherlands and Morocco, he was working out a traveling point heat source model. I mean, all he had was paper and pencil, and he was trying to keep up with his research, and he worked out what's now known as the Rosenthal equation, which is a solution for the traveling point heat source on a plate. So if you're talking about an arc or well, let's just say an arc or a flame moving along the top of a plate, Rosenthal worked out an analytical solution based on this solution right up here. He basically just put this in a moving coordinate system. T minus T0, here he has a Q, which is the heat of the arc, divided by 2 pi K, where this rho C sub P and alpha T has all been, the units have all been reduced to thermal conductivity. 1 over R, which is the same R as we have up here. Exponential V is the velocity that the heat source is moving along the plate, divided by 2 alpha R plus X. So this exponential term changes a little bit. It's moving in the velocity V. Q is the strength of the heat source. So Rosenthal put all this together, published it, and if you go back to the original paper, it's a very long paper, like 20 pages long, where he works out the math on this to get that final result. And that still is one of the simplest and best results that we have for heat flow and welding. Professor Masabuchi told me about a month ago, when Rosenthal's paper came out, he was a student at the University of Tokyo. And this was during World War II, and they didn't have copying machines then, and he was a student studying welding at the time, and he remembers hand copying Rosenthal's paper out of the library. It took him 3 days to write it all down. In any case, well, so that was Rosenthal, and he had that one connection with MIT. He later went out to UCLA and became a professor of metallurgy out there and passed away a few years ago. He wrote a book on physical metallurgy while he's out at UCLA. Then in another World War II story, in Norway, which was not neutral in World War II, but Sweden was, they had Norwegian freedom fighters. And one of those was a guy named Niels Christensen, and he would ski across the mountains from Sweden into Norway fighting the Germans during World War II. After the war, he came over here on, I believe, a Fulbright scholarship, or a Marshall, it might have been a Marshall scholarship. George Marshall was the Secretary of State. He'd been a general in World War II. And to help Europe rebuild, we created these fellowships for some of their brightest students to come over here and study. Well, Niels Christensen came over here at MIT. He worked under John Chipman, and he had been interested in welding, and he did work on welding fluxes and graduated around 1950. About a year late, because he misplaced his thesis, and we didn't have them stored in computers back in 1950. They think, in fact, he told me once, he's passed away now himself, but he told me once they think that a Soviet spy had stolen his thesis. He had it all written, all the data done, and he came back to his office one day, and it was gone, and he had to start all over again and repeat all his experiments. Fortunately, at that point, you know exactly which experiments to do because you've already done them once. But he had to repeat them all, collect the data again, and so he graduated. He worked on welding fluxes, and he went back to Norway and became a professor at University of Trondheim in Norway. In the mid-60s, the U.S. Army and others were still trying, just like we now try to help the former Soviet Union scientists do things. Europe still in the mid-60s didn't have as much scientific base or resource economic base as they would like. So the U.S. military actually was funding research in Europe. And Niels Christensen got a research grant from the U.S. Army. He had some sort of accident in an automobile, and he was laid up in bed for a year. And during that year, he took the Rosenthal equation, he put it in dimensionless form. And so in dimensionless form, theta, which is a dimensionless temperature, divided by something called the operating parameter, 1 over rho is a dimensionless r value, exponential minus rho plus lambda. Lambda is a dimensionless value in x, and rho is the r, so you can see the similarity. Basically, he just took Rosenthal's equation and put it in dimensionless form. You have a copy of his paper from the British Welding Journal in 1966, which won the award. It wasn't the best movie. Oh, sorry, Chris is not here. But in any case, if you put the whole thing in dimensionless form, you end up with a plot that looks like this. This is the temperature distribution, the normalized dimensionless temperature distribution for any traveling heat source, point heat source on a plate, and it looks like a skewed Gaussian. In fact, if you look at it, that's kind of a three-dimensional view. This comes out of Christensen's paper. If you look at slices in different directions, this is traveling in this direction, and you can see the Gaussian is skewed. If you look in the transverse direction, you actually just see the Gaussian, right? So these are just different values at different times, or different Fourier numbers, or whatever you want to call them. Actually, Peclet numbers. There are different types of dimensionless numbers. Looking down from the top, you could define one of these isotherms as your fusion boundary, and that would be the shape of your weld pool, depending on which one you choose. This parameter n, which is the what Christensen called the operating parameter, is a measure. It contains a number of things. You can look at the paper if you're really interested. If I'm traveling very, very slow, then basically the travel speed, this whole thing looks nearly symmetric, and this is nearly symmetric. If I travel a little faster, this thing gets distorted. I travel faster still, I get isotherms that look like this. If I start traveling at the speed of lasers and electron beams, I get things that look like this. So from this, I can look at what distance the heat travels out to the side and whatnot. One of the students, back I used to allow students, instead of doing the homework sets, to do, or a term paper, I used to let them do a project. And one student basically programmed Rosenthal's equation so you could, pop up results. Or the dimensionless form of Rosenthal's equation that Christensen came along with. So those people had a contact with MIT. Then the next major advance in an analytical solution to heat flow and welding came in about 1982. A student here who was working in the room where you have your lunch or have your breakfast, Nunsen Chai, basically took Rosenthal's solution, put it in the Green's function analysis, and so now you can have not a traveling point heat source, but a traveling Gaussian heat source, or any other type of shape of heat source that you want. Because the Green's function basically just takes a bunch of point source solutions and stacks them together with different intensities and gives you whatever distributed function you want. So instead of a point source, you now can have a distributed source. So that kind of there was some MIT connection with those three major advances. Since then, with numerical computers, people are doing all kinds of models of convection in weld pools, which can be important in some cases, fancier heat flow models, but still, since you don't know your thermophysical properties of these high temperature metals and liquids better than about 20 or 30%, you don't really get much better result than you do with these simple solid state diffusion models, as far as that goes. So you can do more sophisticated heat flow models, and people do because it tends to get students a degree. They get a thesis out of it, and we have computers and we have canned programs, and so some student can sit down in a canned program and they'll turn out a paper, and it turns out that there are, I would say, 20% of the people doing research in welding around the world now are basically, it's like anything. Nobody likes to do experiments anymore. They're too difficult, so they just sit down at a computer terminal and do something. I'd say 20% of the papers in welding research now are somebody doing some refinement of heat flow paper, where they're doing convection in weld pools and fancier heat flow. What I do when I'm asked to review those papers now, I don't read the paper. I go directly to the conclusions. And I say, is there a conclusion here that I could not have written before I started to work on this paper? Okay? And invariably, there is no new conclusion. And then I kind of flip to the front of the paper, skim it, and I flip to the figures, see if there's anything new there. And then I write a review and say, there's absolutely nothing new here that couldn't have been written down before they started the research. There's no new contribution to the literature, and I reject the paper. Okay, now that's on the web too. So people will know who's doing that review. Nonetheless, I mean, back in from 1982 to 1985, this was an important area of research. And then maybe there were a couple of little advances through 1988, but since then, for the last 15 years, it's just the same old stuff being beat to death. That's because the longer I'm working in science and engineering, the more I realize how few new ideas there really are out there. Okay? And so, you know, to a certain extent, when someone comes up with something really new and they win a Nobel Prize or they write some seminal paper like Rosenthal's paper that, you know, people have been using for the last 60 years, it really is an important activity. I'd have to say that 90% of all the research, and this goes for NSF proposals or anything else, they're just incremental research. And people are not really being creative like they should. Okay, let's talk, any questions on heat flow? If not, I want to talk a little bit today and on Halloween about lasers and electron beams. So we have time to pass these around before we run out of time. Let me show you a couple of pieces of lucite, just polymethyl methacrylate for all you polymer scientists out there. Actually, not lucite, this is actually plexiglass. Lucite is actually calcium carbonate. But anyway, this is polymethyl methacrylate, just simple plexiglass. And if you want to, if you're dealing with a high power laser and you want to know what your beam looks like, you can basically just pulse the beam into a piece of plexiglass. And this might have been 10 pulses, but you basically evaporate away the energy distribution. So if you want to see the energy distribution, you just turn it upside down, and that's the energy distribution in your beam. What you vaporized, the cavity you vaporized away. If you look inside here, there's a little dimple, like it's a bagel that didn't got so fat that everything came together, and there's just a little dimple in the center. This one was made by Hitachi. I happen to know that one was done at the Edison Welding Institute in Ohio, and that was just a research sample. And I walked through and I said, oh, "Can I have one of these?" They said, "Sure." This one Hitachi did back in the mid '80s, and I was walking through. They gave these away with a little name tag on them. This was a 5 kilowatt laser they had, and the lasing cavity had a diameter of about roughly an inch. So it's a big long tube of quartz with a lasing gas, CO2 and other gases in there. And you generate what's called a multi-mode, and we'll talk a little bit later about multi-mode. You generate the laser and then you shine it with mirrors and you focus this down to a spot. But if you look at it before it's been focused down, you'll feel on the surface a little ripple pattern, bumps. It's got goosebumps. It's cold, okay? No, it's not cold, but it was actually hot. But that is actually the interference and the diffraction spots of the laser in this multi-mode laser. And this one, which is much deeper, all they did was with the mirror, they took that circle and they tilted it to turn it into a sharp ellipse, to turn it into a line scan so you could heat treat with that laser. So this one, if you turn it upside down, this one's not very deep. This one is much deeper, but all they did is they just tilted the mirror, and if you bring a circle in this way against the mirror at an angle, it projects an ellipse. Okay, so all they did was project an ellipse to create a line source. As we say, in laser technology, it's all done with mirrors, right? So if a lot of people think that lasers and electron beams are equivalent joining technologies, and for the next hour's worth of lecture, I want to try to convince you they are not equivalent. In fact, they are almost opposites. They are both high energy density processes. They can both give you 1,000,000 watts per square centimeter, which is, or even 10 to the 7th watts per square centimeter, which is out at the outer limits of the heat intensities you want for fusion welding. If you go above 10 to the 7th, you're going to get into the regime of hole drilling, not laser welding. It turns out with lasers, you actually can get up to intensities, well, with continuous lasers, you can probably get to 10 to the 8th watts per square centimeter, depending on how good your focusing optics are. With pulse lasers, you can get 10 to the 13th watts per square centimeters, where these lasers are pulsing for some nanosecond or something. Okay, but if you divide by 10 to the minus 9, you know, or 10 to the minus 8 for 10 nanoseconds, you can get very big numbers. You know, if you have 10 to the 5th joules in your pulse, and you're only doing it for 10 to the minus 8 seconds, then you get 10 to the 13th joules per whatever area you have. So lasers, pulse lasers, can give you very, very high power densities. Electron beams, typical electron beams have a hard time giving you much more than 10 to the 7th or 10 to the 8th. But again, in pulse mode with very high megawatt beams, which we don't use for lasers, but we use for particle beam weapons, you can also get something like 10 to the 10th. And when you start getting to 10 to the 10th watts per square centimeter, you're not just drilling holes, you're ablating the surface. You're blowing the surface apart. You actually will create micro explosions on the surface, which just cause the thing to bounce off or just peel off chunks of material. So those aren't, getting to the very high power densities are not very useful for welding, but you can with these types of technologies, although it gets kind of pricey to do it. Okay, so electron beams, you're heating with electrons, a stream of electrons, and typically your voltage is going to be 40 kilovolts to 100 kilovolts. Now there are some, I talked about megawatt, you know, million volt electron beam units, and we'll talk about how the voltage affects things later. Here, fundamentally, we're heating with photons, and the energy of each photon is h nu. Here, the electron has an energy of 40,000 electron volts, or 100,000 electron volts. It's one electron times whatever the accelerating voltage is. Here, the photon energy is on the order of 1 electron volt rather than 40,000. So there's like 50,000, a difference of 50,000 in the energy of the, I don't want to call them particles. Electrons are particles, but photons, are they particles or are they waves? You know, I don't know. You have to wait for some other person to come tell you that answer. They behave like both. But the point is, there's a tremendous difference in the energy of each little thing that's interacting with the material. And that has important effects. For the electron beam, you actually get heating beneath the surface. The electrons actually penetrate the surface. For the laser, with very low energy things hitting, photons hitting the surface, everything is on the surface for a conductive material. Now, if I have a non-conductive material, like a glass or something, well, shoot, it can go through it, right? So I could heat beneath the surface of a partially opaque glass or a ceramic with a laser. But for metals, which we're usually interested in welding, it's all surface heating. Does that make a difference? Well, it turns out that it wasn't welding, but at one time, I believe it was Ford, had purchased a laser heat treating machine from a company called Siaki. Siaki was the company, the French company, actually still is a French company, that made the gas tungsten arc welders that the U.S. Navy purchased in the Philadelphia Navy shipyard in 1940 to weld together airplanes when they first started doing electron beam welding. And that was really what brought Siaki to the United States. And now Siaki has an applications group in Chicago, and if you want to spend $3 million for a production welding or heat treating facility, Siaki will build you one, custom engineered. Beautiful equipment, very pricey, but beautiful, okay? Excellent equipment. Well, Siaki, I think it was Ford, I'm not sure, but one of the big three automotive companies wanted to heat treat the surface of the camshafts, you know, the lobes on the camshaft on a car. Remember what a camshaft has lobes. Let's see, I'm not going to draw this very well. That look like this, and they're on a shaft. Then it makes a cam, and as the shaft rotates around, you got the valve lifters that pushes the valve up and down, that goes inside the piston and lets the air in or the fuel in and lets the exhaust gases out. So I've got these camshafts running around, and of course these surfaces, which are hitting the lifters, this surface right here, gets a lot of wear, and so they wanted to heat treat that steel surface to give it a lot of wear resistance. And they first had Siaki build them a machine with a laser, because lasers can work out in the air. They don't require vacuum systems, and if you're making millions of these things, you don't want to have to bring everything into a vacuum system if you don't have to. And it turns out, whenever they looked at the surface of these things, they were getting cracks. Why were they getting cracks? It was surface heating, and if I heat up the surface to 1300 degrees Fahrenheit, which is what I need, or 1600 degrees Fahrenheit, what I need to do to harden the steel, the material on the surface, remember we talked about residual stresses? The material on the surface expands, but the material underneath it doesn't expand, and so it goes into compression. And remember, on whatever happens at high temperature, the exact opposite happens when everything cools back down. So the surface goes into tension when it cools back down. Because that top hot surface went into compression, it actually yielded and changed its shape. Its length was now shorter. When it no longer has thermal heat of expansion and it cools back down, it now shrinks and goes into tension. And they were getting cracks because of the tensile surface residual stresses. So they tried to make it work, they couldn't get it to work. And finally, they said, Siaki said, well, you know, if you go to electron beam, we won't have this problem. Because electron beam actually deposits the heat beneath the surface. I got 50,000 keV particles. They'll go through you. Actually, they won't go all the way through you. They'll go part way through you. Okay. In fact, that's a good cancer treatment. Hopefully, you don't have to go through cancer treatment, but you know, whether they're using radiation or particles, they actually. I keep pointing here because I had cancer 6 years ago, and I have a little scar right here, and I had to go through radiation treatment around my non-Hodgkin's lymphoma, and it's a great sunburn. And in fact, I remember I went to the doctor a year ago for the last time. He says he didn't want to see me because it's been 5 years and I haven't had a recurrence, so I'm considered cured. When they did the CAT scan, he said, well, you couldn't tell anything around here because everything's scarred. And if you hear me cough every now and then, it's because I caught one corner of my vocal cords. And so I have some scars on my vocal cords over here, which caused me to cough all the time. But anyway, so these things have high energies, and they will penetrate through. Over here, they don't have high energies, and they don't penetrate through. Here, you actually heat beneath the surface, and you get favorable surface compressive stresses. And so you wouldn't get fatigue cracks on those surfaces. Okay? So there is a difference. And so they actually did make it work with electron beam. The sample must be conductive with electron beam. If it's not, the electrons are going to accumulate, they will build up the surface charge and repel the electrons coming in. It turns out the laser will heat electrical insulators quite well, in fact better than metals in many cases. Electron beam requires vacuum, and I'll talk about that in just a second, but it turns out the laser is best in helium atmosphere. Why does electron beam require vacuum? Well, you got to shoot these electrons through the air, or through the atmosphere, and you'll have collisions, just like we do in a plasma, right? It turns out there is a process known as out-of-vacuum electron beam. It's been used commercially. A guy named Bert Schumacher was a German scientist who worked very, very vigorously on an out-of-vacuum electron beam welding machine. And he came to the United States, to a place in Connecticut. He worked for Label Jerez, which was a German company. Brought him to Connecticut. Label Jerez cut back, so he went to work for one of the big three automotive companies, namely Ford, and he convinced them to buy these out-of-vacuum electron beam welding machines. And they were using them for the catalytic converters. The catalytic converters in the Ford automobiles, or any automobile, are basically just a clamshell design. You got two halves and you come together like this. And they actually have what we call an omega seal weld. So I've got a clamshell like this, and another clamshell like this. I'm exaggerating the flanges here. And your catalyst is in here, and this is basically the stainless steel can. And you've got to make a seal weld that is gas tight right there on the end. Well, you could do that. You can do a beautiful job with gas tungsten arc at 6 inches a minute, maybe 10 inches a minute. That means for a typical catalytic converter, that might be 2-3 minutes worth of welding time with a fast gas tungsten arc. Plus, you got all the maintenance on the tungsten electrodes, but you may have to replace those every 30 minutes. And so Bert Schumacher convinced Ford that rather than having 100, when you're talking automotive production rates, you'd probably have to have 100 of these or 50 of these setups, just welding catalytic converters over and over and over. And he convinced them they could do everything with a much higher speed because of the higher power density without a vacuum electron beam, and they didn't have to bring things into a vacuum. And they could make these welds at 100 inches a minute or whatever, 10 times the productivity rate, only 100 times the increase in cost. Actually, yeah, about 100 times the increase in cost of the equipment. But nonetheless, he convinced them. They brought in the 6 machines, and they worked good 20–30% of the time. They were being repaired the rest of the time because of all the maintenance on an out-of-vacuum electron beam. You still have to generate the electron beam in a vacuum, and then you shoot it through a porthole and hope that you can shoot the electrons out faster than the air is leaking in, and you try to pump the air away as fast as it's leaking in. So you have a constant leak in your vacuum system. And Bert would tell you how wonderful this equipment was. I once talked to the managers who were in charge of the plant, and all they had to do was curse it, okay, because of maintenance problems. But there is such a thing as out-of-vacuum electron beam, and if you ever meet Bert Schumacher, he will try to sell it to you. That's the only large-scale application I know of out-of-vacuum electron beam. I know a lot of other people have tried it, but I really don't know of anyone else who's really used it. Lasers are best in helium, and the reason they're best in helium, when you have this huge number of photons come shooting down through here, just above the surface, you got metal vaporization coming on. That's what's helping you. It's the reacting metal vapor coming out of the weld pool that's drilling the pressure, is drilling the hole that gives you the deep penetration. It turns out that the metal vapors, if they get heated by the photons coming in, will give off electrons. Once you give off electrons, free electrons absorb laser light wonderfully. And so you'd like to blow that metal vapor away, and typically, if I'm laser welding here, I will have a transverse flow of helium gas. And the reason I use helium because it has the highest ionization potential. It's the most difficult inert gas to strip electrons from. And so if I'm in the United States and I can afford helium for my laser shielding, I blow my vapors away with helium gas to prevent formation of free electrons, which would absorb the incoming light. Number 5 is that if I make a laser weld, and let's say it's 1 inch deep in the vertical position, it'll be 1.3 inches deep if I turn the thing on its side and shoot it horizontally. And the only reason for that is if this is my cavity, and you've now seen the movie that Chris likes so much, this is my cavity. I've basically got liquid slumping down and falling into the bottom of the cavity, and I keep on having to blow that liquid that falls in the bottom away. If I'm going horizontally, now the liquid slumps this way, and I get a free shot down to the bottom of the hole, and that means I can actually penetrate more deeply because I don't have gravity, okay, getting in my way. It turns out with the laser, it turns out you get 50% deeper in a vacuum because you can use a laser out of a vacuum, but if you use a laser in a vacuum, you'll get about a 50% increase in penetration. A little bit better, and you'll get a 30% increase in horizontal. If you were to use the out-of-vacuum electron beam, you're going to find 1/3 less penetration. So really, there's no difference here in how they behave. It really has to do with the fluid flow within the weld pool. The 50% increase in vacuum is due to the fact that the vaporization is more effective if I'm vaporizing into a vacuum than if I'm vaporizing against the 1 atmosphere of pressure. The reactive force, I mean, some of those gas molecules go back down and hit the surface and recondense and things like that. I get deeper penetration if I have a vacuum. I will have inside that cavity, the whole cavity is basically more than 1 atmosphere of metal vapor. I'm vaporizing the metal. It's actually pushing the liquid out of the way and drilling a hole that that deep keyhole is going to be my weld pool shape when I'm all done. It turns out these high energy electrons will penetrate the metal vapor in the cavity. Electron with 50,000 electron volts is not going to be stopped by a single collision with a gaseous metal atom which has a thermal energy of 2 or 3 electron volts. 50,000 versus 2 or 3, 50,000 wins most of the time. You got to have hundreds of collisions before you slow those things down. So you get pretty good penetration of the beam down into the hole, which means the electron beam per watt is going to give you deeper penetration than laser per watt. The problem with the laser is the plasma, the photons will cause some heating of that metal vapor. The metal vapor is pretty hot anyway. If there are any free electrons, those free electrons will absorb the photons, some of the photons, and they'll re-radiate them, and you'll get decoupling. In fact, you get what's called a characteristic nail head shape, which you see both in electron beam and laser, but it's more common in laser. You'll get a weld pool that actually looks like this. And they call this the nail head up here. You've got your beam coming in, drilling a hole, but you've got some defocusing going on up here in the plasma, which spreads the beam out and gives you low heat intensity. So I really got two weld pools. I've got a shallow weld pool, which is the head of the nail, and I get deep penetrating weld pool. Depending on how you set up your beam parameters, you can get the nail head shape, and that's more common in lasers because the photons are more readily absorbed. Electron beam is nearly 100% heat efficient. Measurements show it at 98 to 99% efficient, and that's because you're traveling fast, you're not heating up a big heat affected zone. You will create a heat affected zone, but on cooling, as the fused metal gives up its heat of fusion, as it solidifies, you'll create a heat affected zone as the heat diffuses away. But as you're putting the weld down, you're just melting the metal. There's no time in these very, very high speed processes to heat up the surrounding material to any substantial amount. And the actual loss is actually primarily a vaporization heat loss of 1 or 2%. This is nearly 100% efficient on ceramics, although it may penetrate, it may be somewhat transparent in ceramics, and so it may not be true surface heating. But on very reflective materials, that's supposed to be gold, aluminum, gold, copper, and aluminum, it can be less than 5%. And that's because these are very good mirrors. They reflect light. And in fact, the mirrors typically, for high power lasers, if I'm going to use mirrors to transmit the beam, the high power mirrors are made out of copper because it has good thermal conductivity and will carry the heat away, and then they gold plate the surface. Anybody have an idea why you might gold plate the surface after you made this copper mirror? It has to do with the fact that copper will tarnish and gold will not. If the copper tarnishes, I have copper oxide. Well, the heating of a ceramic like copper oxide is nearly 100%. So if I get some tarnishing and now I hit that copper mirror with a high power laser, I will actually heat up those oxides and I will thermally pit the surface of my mirror. I'll destroy my mirror because it oxidized. Whereas if I have gold on the surface, gold doesn't oxidize and it maintains its good reflectivity, and I only absorb 5% of the heat, which I hopefully carry away through the copper. It turns out, well, actually, that's enough. On Thursday, I'll tell you about 2 patents I ended up with medical instruments that had to do with essentially a laser material that would absorb heat, but conduct it away quickly. And then we'll finish up lasers and electron beams. Okay?